Hello and welcome everyone. In today's lecture, I am going to discuss about the dynamics of reciprocating engines in the subject dynamics of machinery. So basically, in dynamics of reciprocating engine, we are supposed to balance the unbalanced force acting on it. The various applications are in IC engine, reciprocating compressors, and reciprocating pumps. Now, in this lecture, we will be discussing about the balancing of reciprocating masses in single cylinder engines. So, first of all, it involves two parts. First, we have to determine the unbalanced force, either inertia force. Suppose any body is rotating with certain mass, there will be inertia force acting on it. So in reciprocating engine there will be also inertia force acting on it. So then, and another second part is balancing unbalanced force by convenient method. First we have to determine the unbalanced force and then balancing the unbalanced force by convenient method. So first let us check the various unbalanced force in primary in reciprocating engine. There are two types of unbalanced force in reciprocating engine. First one is primary and second one is secondary unbalanced force due to reciprocating masses. So as we know that the acceleration due to reciprocating mass of single slider crank mechanism is given by omega square r into cos theta plus cos 2 theta by n. Omega is the angular velocity, r is the radius, and cos theta, the theta is the crank angle, and n is obliquity ratio L by r. So the inertia force due to this acceleration will be equal to Fi is equal to m omega square r cos theta plus cos 2 theta by n. So as we know that the force is equal to m into a. Force is equal to m into a. So the unbalanced force will be equal to the inertia force, and here the inertia force is equal to mass into acceleration is this f omega square r cos theta plus cos 2 theta by n, and here the unbalanced force fu is equal to fi. Inertia force is equal to unbalanced force. The first part of inertia force is called as the primary unbalanced force, and the second part is called as the secondary unbalanced force. Now the unbalanced force will act in the line of stroke and its direction will be opposite to the acceleration. Suppose the direction of motion is in this direction, the unbalanced force will act in this direction. Now the primary unbalanced force is due to the simple harmonic motion of reciprocating part. Due to the simple harmonic motion, the primary unbalanced force m omega square r sine cos theta will be acting. Now the value will be maximum at 0 and 180 degree. The as we can see, this is the equation of primary unbalanced force m omega square r cos theta. Now this will be maximum at 0 and 180 degree. So the primary unbalanced force will be maximum at 0 and 180 degree. That means that twice in one rotation of crank. As the crank rotates one revolution, there will be 2 times maximum value of the primary unbalanced force. Now the secondary unbalanced force is acting due to the obliquity of arrangement. Due to this, there will be four values which are maximum at angle 0, 90, 180 and 360. That means the 4 times in one rotation of crank. This is because so the we can say that this is the frequency of primary unbalanced force is twice the frequency of ठीक है जो frequency, that means the secondary unbalanced force is twice the primary unbalanced force, but its magnitude is 1 by n times of primary unbalanced force. As we can see in the equation over here, the magnitude is 1 by n times the primary unbalanced force, and its frequency is twice the primary unbalanced force. Now in case of low and moderate speed, this can be neglected as it is very small. The secondary unbalanced force is small, so we can generally neglect in. So now only the primary unbalanced force has to be balanced, as the secondary force can be neglected for low and moderate speed, but for high speed it is to be considered. Now let us discuss the difference between the unbalanced force due to reciprocating mass and rotating mass. रोटेटिंग मास एंड रेसिप्रोकेटिंग मास में जो difference that we have to discuss: reciprocating and rotating mass. Now the unbalanced force due to reciprocating mass varies in magnitude but constant in direction. As we have seen, it is acting in the direction of piston movement, which means it is acting in the line of stroke. The unbalanced force due to reciprocating mass is constant along the direction of line of action, while it varies in magnitude. It varies from 0 degree to 180 degree, maximum to minimum value. While for rotating mass, the magnitude is m omega square r, which is constant, but the direction varies because it is rotating, so the direction will be varying. Therefore a single mass cannot be used to balance reciprocating mass completely. So we cannot use a single mass to balance reciprocating mass completely. So single rotating mass can be used for partial balance of reciprocating mass. That means we have to partially balance the reciprocating mass. Now as you can see over here, the partially unbalanced force is equal to Fp m omega square r. Now this will be acting in this direction, Fp m omega square r, and this is the length, this is the crank rotation omega, and this is the angle theta. O is the center. Now here what will happen? The unbalanced force will be acting like a, suppose here there is a mass which is to be balanced. Its magnitude is equal to m omega square r. So this primary unbalanced force, we can assume that it is acting like a single rotating mass with a angular velocity omega, and so if we take the horizontal component, it will be equal to the m omega square r cos theta, which is our the primary unbalanced force. Now we have to consider the effect of this balancing effect of the balancing mass. So this is our unbalanced mass m at the crank center c, and which is rotating with omega angular velocity, and we have to balance, so we are adding over here the balancing mass m b at radius r b. So what will happen? Due to this, there will be primary force F P, which is equal to the m omega square r cos theta. Now due to adding this balancing mass, there will be horizontal component acting will be equal to the mb rb cos theta. So what will happen? This primary force will be balanced by this horizontal component, but there will be the vertical component will remain unattained. There will be mb rb sin theta component will be acting in this vertical direction. So there is only change in direction. There was the primary unbalanced force was acting in the line of stroke. Now we have, by adding the balancing mass, we have only changed the direction of acting it. So this will there will be the effect of unbalance. So we are doing the partial balancing, so we can reduce the effect of this vertical component and also balance the horizontal component. So we, in the next portion, we will be only balancing the some fraction of the primary unbalanced force. So here we are, the primary unbalanced force is equal to cos theta. So c is the fraction in the amount which we this is the our balancing mass, and this is the our primary unbalanced force. Now we are balancing in a some fractional amount where the c value of c will be less than 1. So the balanced primary unbalanced force is equal to c m omega square r cos theta. Now the unbalanced force due to partial balancing in horizontal direction, there will be the fp m omega square r cos theta, and the balancing mass can be subtracted mb omega square rb cos theta. So the we don't know that the we are partially balancing, so we put the value over here. So we get the horizontal unbalanced force is equal to 1 minus c m omega square r cos theta. And same way, the vertical component due to the balancing mass, it will be equal to the mb omega square rb sin theta, and fv will be equal, as we know that the mb rb is equal to cmr. So we can find the resultant unbalanced force, which is equal to under root fh square plus fv square. So our final resultant unbalanced force will be equal to m omega square under root 1 minus c square cos square theta plus c square sin square theta. Now this force will be minimum at if we do the derivative of it with respect to c. So it will be minimum for the value c is equal to 1 by 2. So the unbalanced force is minimum for c is equal to 1 by 2. But as we know, for locomotives, the value of c is 2 by 3 to 3 by 4, which is slightly higher than the this value, because the reason is that the horizontal force is much more important than the vertical. The effect of vertical force is much more in as compared to the horizontal force, so we cannot increase the vertical force. So the final primary balancing will be equal to the partial balancing plus rotating balancing. So balancing mass is equal to cmr plus mr rr. Let us consider this with an example. Suppose a single cylinder reciprocating engine which has a speed is equal to 240 rpm and the stroke is given 300 mm. The mass of reciprocating part is 50 kg and rotating part is 30 kg, revolving part, and the radius of rotation is 150 mm and the balancing mass radius is given 400 mm and the value of c is given 2/3. So theta and theta is equal to 60. We have to find the unbalanced force for theta is equal to 60. So first of all we have to find the omega angular velocity is which is equal to 2 pi n upon 60 that we can find. And as we know that this is the equation of primary balance, MBRB is equal to CMR plus MRR. So this is the, so here there is the we have to convert the radius into mm to meter and we can find the balancing mass in kg, and the unbalanced force we know the equation. By putting the value we can find the unbalanced force. So so by C and theta, here the theta angle will be equal to the 60 degree and mass is given which is equal to the 50. Omega is the angular velocity we have find, and r is the crank radius that we can find from the stroke. Stroke is equal to, here the stroke is equal to 2 times r radius. So we can find the crank radius. Thank you very much.